All right, next we're going to fixate on what's called the single slit diffraction pattern. So as you'll see in the lab, it turns out that if you bring in a laser beam from the left like we were doing last time, and you shine the light through just one opening, so now you just have a barrier here and here with this opening in the middle, and you look at what happens on the screen. It turns out that, again, instead of getting, like, say, a single spot behind where the light gets through, instead of getting that, again, you get this surprising pattern of bright and dark spots. Looks kind of like this. Now, this is a little different looking than the single slit pattern. One thing that's different is this central bright spot is kind of doubly wide, okay? So, in other words, if you were to look, you notice this is going like bright, dark, like this. If you were to say, pick on the dark spots, here's a dark place, here it's dark, here it's dark, there's a certain spacing here. Notice if you were to repeat that, you would end up kind of in the middle here. Okay, so notice you have dark, 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 and then if you followed that exact same distance, it's sort of like, should be dark there, but we know that it can't be dark because that's at the exact middle of the pattern. So this central bright spot is actually like doubly wide in this single slit pattern, okay? Well, so what you can do with this to try to get a sense of why does it look like this and get a sense of the geometry, what's really going on is each little bit of light that passes through here, you can think of each place the light gets through as like a new source of light waves, okay? And so what's a little bit beyond what we're able to do at this point in physics 2 is really what you need to do is add up all these little infinite sources of light that are all along here, because these are all the places where the light actually gets through. If you add them all up, it turns out you can derive this pattern, right? You need calculus for that, which we're not going to do. But what we will do is look at another scheme for kind of getting it, and that would be to add these things kind of like pairwise. And so the idea would be to take sort of this first place where the light beam gets through here, and then pair that with a place right below the center where the light gets through. So in other words, you consider this pair, then consider the next pair, and the next pair, and the next pair, until you're all the way down through the opening, okay? Well, so if you start with this, and you consider these two places, where this is just below the top barrier and this is just below the center, you can kind of think of these two sources of light conspiring to make, and here it's going to be a dark spot, okay? And so what you do is you'd say, well, why would it be dark at that place? Well, you know that when you're here, your delta path would be half lambda. Here it would be 3/2 lambda, and so on. 5/2 lambda up here, okay? Or n plus 1/2 lambda for dark spots. So our condition for destructive interference is delta path equals, well, for the first dark spot, it's going to be half lambda. So I'll say 1/2 lambda for first dark spot. Dark, not dark, spot. Okay? So it's half a wavelength there. Well, what we need to do then is let's work on this other side. Well, how big is the path difference? So really what we need is this extra itty bit of length, right? Which if you blow it up over here, that's this extra itty bit of length. This is your path difference right here. So this length is important because it's how much farther one had to go than the other, or this is the delta path. And what you can see from the picture is if we know this length here is d over 2, and this is theta, well, again, this is the opposite side of the angle that we know, so this must be d over 2 sine theta. Okay, so we'll just put that in for the path difference. So we get d over 2 sine theta is lambda over 2. Well, you notice the 2's will go away. And so what's kind of neat with this is you get d sine theta equals lambda for the first dark spot, okay? And so it's really the same equation that we got for the single slit pattern, only it was for bright spots. In fact, that's why we kind of set it up this way. So if you want all the dark spots, so the thing to know for the single slit pattern, okay, so to generalize this, for the single slit pattern, it's d sine theta equals m lambda, but for the dark spots. So that's one difference between you. So you get to use the same equation, it just has a different meaning for the single slit pattern. It'll find all the dark spots for you. And again, by looking back at this picture, this angle, the tangent of this angle, is opposite over adjacent, or x over L. So maybe I'll just put that down here. That it's still the case that tangent theta is x over L. So you get to use these two relationships for both the single slit and the double slit. It's just that for the single slit pattern, it finds the dark spots, where for the double slit pattern, that exact same relationship finds all the bright spots. So just realize that's going to be the case. Again, if you're kind of thinking of the pattern, the single slit pattern has a central spot that's doubly wide. The double slit pattern has a bunch of evenly spaced spots, right? And we'll see that in the lab as we do these experiments with both the single slit and the double slit. All right.